So we're right on time. So it's 12:25 Eastern time. So welcome everybody then to the last session of today. And so Roberto De Carli will be the moderator. So please take it away, Roberto.
Hi everybody. Thanks for joining again. And yeah, I'm Roberto De Carli. I'm staff astronomer at the observatory INAF Observatory in Bologna. I have the pleasure to be the moderator for this session. And with this, I think, without further ado, I think I would like to invite the first speaker of this last session of today. It's Julien Wolf.
Hi.
Hey. The floor is yours.
Thank you very much. And thank you to the organizers for the great conference so far. So I'm Julien, I'm a third-year PhD student at the MPE, where together with my supervisors, Paul Nandra and Mara Salvato, I'm currently working on the search for high redshift quasars with eROSITA. And I'll present our most recent results. So with the soft X-ray sensitive eROSITA sky survey, what we hope to uncover is the most X-ray luminous population of quasars right at the end of the epoch of reionization. And if you look at this eROSITA sensitivity, hard X-ray luminosity redshift plane here, you see that beyond redshift 5.5, we're essentially only sensitive to the most X-ray luminous AGN, beyond 10 to the 45 ergs per second. So our approach to sample this rare and extreme population is twofold. First of all, we are, of course, looking into detections of previously known spectroscopic high redshift quasars in the eROSITA data. And second, and I'll focus on this point more today, we are searching for new X-ray luminous quasars in the eROSITA Old Sky Survey, which we also call ERAS. So if you're interested in the detection of previously known high redshift quasars in the eROSITA data and about the consequences for the X-ray luminosity function, I'd like to point you to the full-length version of this talk, which I have uploaded. Here, I will only talk about the detection of one particular source we're currently working on. And this will connect with the narrow-line quasars that were mentioned by Michael Strauss yesterday. So for this, we have to relocate to the EFEDS field, which is a deep performance verification survey that was carried out early on by eROSITA. And in this deep eROSITA field, we have detected soft X-ray photons from a low luminosity shell Q's quasar at redshift 6.56. So the source is detected in the eROSITA EFEDS catalogs, albeit at a low detection likelihood. So we confirmed the detection with a 21 kilosecond follow-up observation with Chandra last October. So the quasar itself was initially discovered by Matsuoka et al. In 2018 and has the peculiarity of being extremely Lyman alpha luminous. In addition, from Subaru spectroscopy provided by our collaborator Masafusa Onoe, but also from published spectroscopy from Yang et al. In 2021, we know that this quasar has a narrow MG2 line, accretes at super Eddington rates for a relatively modest black hole mass. The hard X-ray luminosity that we derive from the Chandra events at about 2 times 10 to the 45 ergs per second is extremely high for such an optically faint quasar. So the picture that arises here is that of a super accreting narrow line Seyfert 1 type of object at high redshift. And we might just be observing a supermassive black hole in an early evolutionary stage. And this is investigated further in this paper we're currently working on. So I'll move on to the second method, which is really aims at discovering new X-ray luminous quasars in the eROSITA All Sky survey. And for this, we have developed a selection pipeline, which focuses on the dark energy survey footprint. So the selection pipelines consist of multiple selection stages, the first one being a very loose color pre-selection in the DESDR2 catalogs to get optical dropout objects. These optical dropouts are then processed by a set of 2 filters, independent filters, which really aim at reducing the contamination by galactic cool dwarfs, the main source of contaminants in this type of searches. So we obtain a sample of 438 optical infrared candidates that we further down select by requiring eROSITA all-sky survey detection. And I'll walk you through each of these building blocks of the selection. The first one, the first filter, is a classical photometric redshift computation using DES, VHS, and QGACT2022 photometry. We simply compute photoses very classically in the LOFAR photometric code, only keep high redshift quasar candidates for which the QSO model significantly outperforms the stellar model in the SED fit. Our second filter is something close to what Lena Lenz has presented before, a random forest spectral classifier. This is a machine learning classifying model that is trained to map from DESDR2 and QATWISE2020 photometric features to a set of spectral classes, among which we have high redshift spectroscopically confirmed quasars, LMNT dwarfs, but also SDSS DR16Q quasars. So once trained, this model reaches very high precisions, as you can see here from this confusion matrix that we obtain from an independent test set. So we have a filtered sample of dropout candidates. We can now check for eROSITA detection. And this we do in two ways. The first is by matching to an ERAS QATWISE2020 counterpart catalog that we have produced using the Bayesian cross-matching algorithm NWAY. And simultaneously, we perform forced photometry at the optical position of the quasar candidates on the stacked eROSITA images. So we have a set of high redshift quasar candidates detected in eROSITA. We submitted 9 of these high priority sources to collaborators at the Magellan Clay telescope for spectroscopic follow-up. Out of these 9 high priority sources, we can confirm the discovery of 5 new redshift greater than 5.6 quasars in the eROSITA all-sky survey, so X-ray luminous quasars. 2 of them are particularly interesting. Here you see their smooth eROSITA images.
2 minutes.
Thank you very much. Because they're also detected in the low frequency radio wave bands of ASCAP. And both sources are confirmed radio loud, which makes them very rare and interesting laboratories for the study of this corona jet interactions at high redshift. One important diagnostic for this type of task is to look at the relative X-ray to UV emission. And this is usually done by computing the 2-point spectral index alpha OX, which is known to correlate with the UV luminosity for the bulk of the quasar population. And this correlation is shown in this plane here. In addition, I'm showing the eROSITA sensitivity at redshift 6 or so. And as you can see, by selection, the eROSITA detected quasars will systematically lie at high alpha X values, flat alpha X values for any given UV luminosity. This means in particular that we have a strong X-ray excess with respect to the UV emission compared to the rest of the quasar population. And indeed, if you look at these squares here, these are all eROSITA detected or discovered quasars. From the German and the Russian side, you see that they all cluster at flat alpha X values. So we have a strong X-ray excess. And this is something that we are and the origin of this X-ray excess is something that we're currently investigating in this publication that will show up a bit later this year. So right now I've reached the end of my talk. I'm leaving you here with my conclusions, with also what we're looking forward to here. I thank you very much for your attention. I'm happy to take your questions. Thank you.
Thanks a lot, Julien. That was perfectly on time. We have question from Girish Kulkarni asks, what fraction of narrow-line quasars has been detected in X-rays, and where do these objects fall in the X-ray luminosity function?
So narrow-line quasars, as in X-rays, so far, I don't know more than the one that we have reported here, but I might be missing some source. And what was the second part of?
And where do this object fall on the X-ray luminosity function? I guess compared to lower redshift quasars.
So this is very interesting. So this is maybe the surprising results here. As you can see, so I'm missing. I've not shown this plot. This is some extra material. this shell Q's quasar we have discovered, which we consider narrow line, has an extremely high X-ray luminosity. So it would really land at the bright end of the XLF at high redshifts, and so really push the XLF up as with respect to what is currently predicted by current XLF models, which I think go until redshift 5.
Okay, thanks. There are a lot of questions that I will probably point you to for that luck. I will just give you just one more, if you can be very quick. From Sarah Bosman, it looked like one of your new quasars was a strong broad absorption line quasar. Is this surprising considering the BALs are usually X-ray weak?
Yes, indeed. So that is actually one of the two radio loud quasars also, for which we are currently also looking into the Blazar hypothesis. We were also surprised by these broad lines and currently investigating it.
Thanks a lot. That was great. Next talk is by Jan-Torge Schindler. He will talk about insets on quasar evolution. Please.
Yeah, thanks. I want to thank the organizers for this wonderful conference so far. And today I will present you with a summary of the insights into quasar evolution in the first 2 billion years of the Big Bang. So I'm currently a postdoc at Leiden Observatory, and here are some of my lovely collaborators. Now this talk has 2 parts. First, I want to look at the quasar population, and then I want to look into quasar properties and their evolution. We understand the quasar population by basically measuring the main statistic, which is the quasar luminosity function. And here you can see the quasar luminosity function as determined by SDSS alone. The line that you see is basically a parametric fit from Kulkarni 2019 at redshift of 2.5, which should serve as an optical comparison. And you can already see the first glimpse of the evolution of the quasar luminosity function here. But at the faint end and the bright end, as well as at higher redshifts, there are still areas that are white on this plot. Now, that's where additional surveys need to come in to provide more information. And I want to highlight the contribution of the extremely luminous quasar survey at intermediate redshifts at the bright end. This is a survey that I've designed particular for this focus, and I used SDSS 2-mass and WISE photometry using a random forest selection to discover more quasars in this redshift range and provide the most complete census. So here you can see the footprint and our known objects shown in blue. We discovered 109 new quasars in this redshift range with a total sample of 407. So 25% of them were new, allowing us a good constraint on the bright end of the quasar luminosity function in these redshifts. We find that the bright end slope is quite steep with little evolution across this redshift range. Now, of course, there are many more studies filling in the gaps at intermediate and also higher redshift. And now I want to focus at the very highest redshift for 1 second. So here at the redshift frontier, this is the situation in 2016 with the samples from Willett and Zhang. With the ShellQ's project, Matsuoka determined the quasar luminosity function with 110 objects using the bright samples from Zhang and the faint quasars from ShellQ's. Now, at the highest redshift, we have the quasar luminosity function determination from Fei Guang from 2019, but there is one quasar survey missing here, which is the PANSTARS 1 distant quasar survey designed by Eduardo Bañados. I'm currently working on a new estimate of the quasar luminosity function, and here are our very preliminary data points. Now, if you want to compare this to one of the other studies, the apt comparison is between this study and Zhang 2016, where you can see we already doubled the number of known quasars so far in this luminosity and redshift range, which will provide us with the most precise redshift 6 bright end quasar luminosity function measurement. Now we can add this data to this entire plot, and it basically shows you visually already the evolution of the quasar luminosity function. From redshift 0 to redshift 3, we find more quasars with higher space densities and more brighter quasars. From redshift 3 to redshift 7, the quasar luminosity function decreases, the number density of these objects falls. Now, this is basically a summary of 10 billion years of quasar luminosity function evolution. It took many quasar surveys, large and small, like the ELQS, to constrain it. From this, we learn that the density peaks at the cosmic noon and then declines exponentially. and even stronger potentially at highest redshifts. We also learned that from these high redshift quasar luminosity function studies, they suggest that quasars play a subdominant role in hydrogen reionization, which we also get from our new in-prep work. Now, at the very faint end, we have some more work to do, and especially in the next few years, it is time to reconcile the studies that have currently constrained this particular range. Now I want to switch a little bit and go to quasar properties and their evolution specifically at the highest redshifts. Here, this is only possible with new near-infrared spectroscopic samples of high redshift quasars, and I just want to list a few of them here. I want to particularly highlight our work with the X2 ALMA sample on quasars in the epoch of reionization that I've been leading with paper 1 in 2020, with paper 2 coming out this year, led by Emanuele Farina. So if you look into the black hole mass bolometric luminosity plane, which tells you about the accretion properties of these objects, the high redshift objects shown here as colored symbols are basically all close to the Eddington limit, or the majority of them. And we have already high black hole masses of 10 to the 8.5 to 10 to the 10 in these high redshifts. If the accretion properties show that these objects are more rapidly accreting compared to equal luminosity lower redshift objects. And if we project the growth back in time with standard black hole growth models, we find that they cannot be produced by the remnants of POP3 stars. Now, so either we need a more efficient accretion process or other ways to produce more massive black hole seeds. And I think this is an extremely interesting puzzle for the upcoming years to solve. We further looked into the enrichment of the broadband region, specifically by iron, using the iron-2 over magnesium-2 flux ratio, which is basically a proxy for the alpha over iron abundance. And so at the highest redshift, we don't expect iron yet to be existing in the ISM. Now, from the evolution that we can constrain so far up to the highest redshifts, we find the ratio to be non-evolving, which indicates at face value that a rapid iron enrichment has to happen within the first 0.7 to 0.8 gigayears of the universe.
2 minutes.
And from other studies, we know at the same time that in these objects, the broadband region metallicity is already high. The last thing that I want to highlight in a comparison between high redshift composites and low redshift composites is the feature of the carbon-4 line, showing this symmetry here that is often associated with outflowing gas. We also looked at it in our higher redshift sample, and here is a redshift evolution of the carbon-4 to magnesium-2 velocity shift. Now, the first time we saw an evolution here was in the study of Meyer et al. In 2019. And with our high redshift samples coming in here, we see that on average, these samples show that these higher redshift quasars more commonly show large carbon-4 magnesium-2 velocity blue shifts, which could indicate strong broadline region outflows at the highest redshifts. Now, there are many questions that are coming from these studies. And I think the future really is really bright for quasar science in the next couple of years. Especially Euclid and LSST will open up the discovery space for these high redshift objects, especially at the faint end, where we trace the bulk of the quasar population. And with the James Webb Space Telescope, we'll get unprecedented data that allows us for the first time to look at the rest frame optical properties of these high redshift quasars. And with that outlook, I want to leave you and thank you for your attention.
Thanks a lot. That was really perfectly timed. I don't see questions yet, so maybe I can start with one. We've seen this. You showed in the plot that the problem, the tension we have with the black hole mass growth. My question is, where do you think we should push to understand better what kind of black hole seed we should consider? Do you think we should push toward a higher redshift, so you get to tighter and tighter constraints, or you go or it's better to go to a fainter population of the GN that might be more representative of the bulk of the intrinsic population?
I think you already gave the answers. I think both, actually. So the highest redshift objects allow us to constrain basically the maximum mass that or provide us with the strongest constraints on this maximum seed mass. But to understand really the population of the seeds, we really need to understand also the full entire population of these high redshift objects. And there, especially at the faint end, we have yet a lot of work to do.
Thanks. So we have a question from Valentina Dodorico. How much of the flattening of the low luminosity end of the luminosity function at redshift larger than 3 could be attributed to completeness problems?
So we're talking about these parts. Yeah, I think this is also a very interesting part in the sense that, for instance, a study by Akiyama et al. Here, this is based on photometric selections. And so you see this discrepancy between the Glickman work as well. So I think this is also a part, one of the things that I highlighted where we need to reconcile these studies in the next few years by basically using LSST and Euclid to also study the faint population from cosmic noon up to the epoch of ionization. So we try to, in all our high redshift studies, we always try to correct for completeness as much as we can, but we're limited to some point by the photometry that we have, and these deeper photometric surveys will allow us to provide better answers, I think.
Thanks a lot. I think we have one more question, but probably it's time to move towards the poster session. I'll suggest that you check it in the Slack.
Thanks.
Thanks a lot. So we have now the poster session. All the speakers will present and will have 1 minute to present their poster. And the first one in the list is Raúl Bayer.
Yes. Hi, everyone. My name is Raúl Bayer. I'm from Universidad de Concepción in Chile. And this is my project, a potential 1,000 offset between the 1,000 kilometers per second offset between the C2 and Lyman alpha line emission in a star-forming galaxy at very high redshift. This is at redshift 7.2. What we did was observing the galaxy through the C2 emission, the galaxy GN108036. And we have a 3 sigma significance levels. And what we can observe in the left panel of the figure is the offset between the Lyman alpha detection and the C2 emission. So this is the largest velocity offset report to date, and is in the order of 1,000 kilometers per second. This can explain in a scenario of a large column density of the hydrogen, or in the scenario of the outflow into the galaxy. Also, we detect the galaxy with an spatial offset in the order of 4 kiloparsecs with respect to the UV and HST detection of the galaxy. But this is a behavior report in other high redshift systems. So if you can see the poster, you are invited to see the more detailed.
Thanks a lot. And next we have Sofia Campo.
Yes, hi everyone. I'm Sofia Campo, a master student from the University of Pisa, and here I present briefly my work thesis done in collaboration with Professor Dodorico, Professor Messinger, and the QGACT2022 team. Our aim is to derive updated and more stringent limits on the neutral hydrogen fraction at redshift around 6 using the QGACT30 sample. To do so, we used the model-independent method of the dark pixel fraction, which was developed by Messinger in 2010 and then implemented by Mekier et al. In 2011 and 2015. We estimated the dark pixel fraction in the Lyman alpha and in the Lyman alpha forest of each spectra, because that's where the remaining neutral patches along the line of sight of distant quasar will generate dark pixels. And with this work, we obtained great improvements since previous works, which are consistent with our results within 3 sigma. And we also obtained less stringent limits than before, which are in better agreement with the recent models provided by Quinn et al. In 2021. Thank you.
Thanks a lot. Next is Huanqing Chen.
Oh, hi. I'm Huanqing Chen from Chicago. I'll talk about measuring the density environment of reionization epoch quasars using the absorption spectra. Understanding the quasar environment is very important, yet it is very challenging for reionization epoch. In today's talk, we have seen many studies using galaxies as chasers to recover the density environment. In this study, we tackle this problem from a new aspect. So we are using the Lyman alpha absorption spectra in the quasar proximity zones. We developed a method to recover the density field, and then we test it against the simulations and find that this method is indeed very accurate with small scatter. Then we apply this to the extended XQR30 quasar sample, and we study the density cumulative distribution function at different distance bins, and find that the density field closer to the quasar is significantly higher. And this indicates a typical host halo of bright quasars at redshift 6 is around 10 to the 12.5 solar mass. And welcome to my poster for more details.
Thanks a lot. Next in the line is Aniek Ludeman.
Hi, everyone. My name is Aniek Ludeman, and I'm a PhD student at the LIDA Observatory in the Netherlands. And in my poster, I show you the preliminary results of an observing campaign that we started looking for radio loud high redshift quasars by combining the legacy survey with the LOFAR 2-meter sky survey. And here we have conducted spectroscopic observations to confirm our candidates, and this led to the discovery of 20 new radio loud quasars between a redshift of 4.9 and 6.6. And with this campaign, we had a high success rate of 33%, which is due to radio detections removing a lot of the stellar contaminants. And one of the interesting things that we find is that our quasars are actually very similar in color and other optical properties to the known quasar population, which might suggest that there is no strong radio loudness dichotomy. So to conclude, our campaign demonstrates the potential for discovering new faint high redshift quasar population using the next generation of radio surveys. So if you're interested, please check out my poster, and thanks.
Thanks a lot. And next we have Yanqi Liu.
Hi everyone, I'm Yuan Qi from Peking University. Our work is to constrain the quasar radio loud fraction of at redshift 6. So we got a much larger and less fast sample at redshift 6 with new VLA observations, and we got the results about 10%. It shows no clear difference with the low redshift quasars, so there's no clear trend of evolution. And also there is no clear difference between optically luminous and optically faint quasars. And then we got a VLBA observation follow-up of the newly categorized as radio intermediate quasar 2012, this quasar here, and we find 5 sigma possible wake jet here. So it's quite interesting. So if you are interested in it, please check our poster, or also you can scan the code here and to get the paper. Thanks.
Thanks a lot. Next we have Cristobal Moya.
Hello, I'm Cristobal, a PhD student at Pontificia Universidad Católica de Chile, working with Professor Felipe Barrientos. What we are trying to do is to study the nature and particularly the escape fraction of Lyman alpha emitters from the Lagrange survey, meaning a redshift around 6.9. Here, to do that, we take medium resolution near infrared spectra, looking for emission lines to get a systemic redshift, as well as trying to resolve the Lyman alpha profile. Here I'm showing you the first reduced data product from our campaign, on which we were able to resolve Lyman alpha profiles into 2 distinct peaks. We modeled the profile using Flareon and obtain a high Lyman alpha escape fraction as well as a low column density, meaning that the source could be Lyman continuum leaker. In the future, we wish to analyze more of this profile and hopefully measure the average escape fraction of Lyman alpha emitters at this redshift. Please check out my poster if you are interested in the details.
Thank you very much. Ana Carolina, Pozos Nascimento.
Thank you. Hello, Hello, everybody. I'm Ana Carolina, a PhD student in Universidade Diego Portales, and I invite you to check my poster. We study in high-resolution observations the C+ line emission of this very interesting typical star-forming galaxy called 2987. It shows signs of being supported by rotation in a moment that usually we see more disturbed and clumped systems. And mainly we study the C+ and UV spatial distribution. We study the C+ dynamics and the C+ and UV surface density. And we could see a complex environment. We could see indeed a disk in a short stable phase and no C+ efficiency, unlike other galaxies at this redshift range. So if you're interested, contact me and we can discuss in more detail. Thank you.
Thank you very much. And next we have Sofia Rojas Luis.
Hello, everyone. I'm Sofia. Okay, I'm Sofia Rojas, and I work at the Max Planck Institute for Astronomy. And earlier today in the first session, we heard a lot about overdensities around quasars, and I'm wanting to show this one that I'm studying. So this quasar at redshift 7.54 is one of the most distant and most luminous quasars that we found. And therefore, we believe that quasars live in this most massive dark matter halo. So we are expecting to maybe see some galaxies around it. And for this, I use HST data, specifically these 3 filters, to look for high redshift galaxies using the Lyman break technique and also some color technique. The most important thing to note here is that you need a filter that is like in bluer wavelengths so that you can see the break from the Lyman break. And then you keep seeing, for instance, the quasar as you see here in these images. I have some preliminary results, specifically of these 4 galaxies that seem to be aligned with a large scale structure that could be part of this overdensity. The 4th galaxy here has been previously selected in a C+ search by Beneman et al. 2020. However, we see a little bit of emission in the bluer filter, so we still need to investigate a little bit more. Unfortunately, we also have IRAC imaging in 3.6 and 4.5 microns for all of these, for the whole field of about 1 megaparsec, so we can constrain much better if these are real high redshift galaxies around this quasar, which will define it as an overdensity.
Thanks
so
a lot.
Thank you, and please ask me more questions later.
Thanks. And we have Sander Schoos.
Hi, my name is Sander Schoos. I'm a PhD student in Leiden, and our poster highlights an interesting result from REVELS. REVELS is a 70-hour large program on the ALMA telescope targeting 40 luminous UV-selected galaxies in the epoch of ionization. We target their C+ lines and their disk continuum to obtain their redshifts and study the physical conditions. What I show here and on my poster are the results for the C+ star formation rate relation. And we find that there doesn't seem to be a significant evolution all the way from redshift 0 to redshift 8. And that is interesting because we of course know that the conditions in these high redshift galaxies must be different from low redshift. For example, lower metallicities, higher gas densities, and higher ionization parameters should actually lower the C+ emission. So there must be a competing effect that compensates for this. And one of them could be a decrease in the dust to gas ratio. And that's what I show on the right side here. What we observe is increased C+ over far infrared emission compared to low redshift galaxies. And that further points to a lower dust to gas ratio. And the dust to gas ratio increases the size of PDR regions because the dust opacity is lower, and that increases the C+ emission. But to study this in more detail, further studies are of course necessary. So thanks.
Thanks a lot. And we have now Joris Witzok.
Yes, hi everyone. My name is Joris Witzok. I'm a PhD student at the Kavli Institute in Cambridge. So recently with my supervisors, Renske Smit and Roberto Maialino, we've obtained new ALMA band 8 observations of where we targeted the oxygen 3 88 micron line, in addition to existing C2 data that are available for 4 star-forming galaxies at a redshift of 7. And of course, with that also comes the measurements of the dust continuum, where we probe the far infrared SED at 2 different wavelengths. So if you're interested to see our results, have a look at the poster, write to me on Slack, and keep an eye out for the paper that should hopefully arrive in the next few months. Thank you.
Thanks a lot. So I think now we only left with the contribution by Jess Broderick that was recorded because he couldn't be connected now.
Hi everyone, my name is Jess, and I'm presenting a poster on behalf of an international collaboration searching for very distant, powerful radio galaxies. We've developed a new selection technique for finding these rare systems. We use the wideband low-frequency gleam radio survey from the Murchison Wide Field Array, and we select very distant radio galaxy candidates based on their low-frequency spectral steepness and curvature. So we conducted a pilot study with this new technique, and we discovered the second most distant radio galaxy currently known at a redshift of 5.55. We've also identified another rather mysterious source which could potentially be at a redshift of about 8. We've now expanded our pilot project into a much larger follow-up study. Our sample of 51 new ultra-high redshift radio galaxy candidates is currently being followed up with a variety of telescopes, including, for example, with the VLT. Please take a look at my poster for further information, and thank you very much.
Okay. I would like to thank all the speakers of the session. Everybody did an amazing job, and I would like to apologize for butchering most of the names of the session. My pronunciation is terrible. And with that, I guess we can move to the discussion. So you might have seen that I put some ideas of potential discussion in the Slack channel, but I would probably can show you a couple of slides just to have it as a background. Of course, this is not meant to be a one-way discussion, so I would like to invite all the speakers that are able to connect to join, and of course everybody that would like to comment, to use the Slack channel or the Q&A to bring up their contribution. So let me share this. Now you probably don't see much. So you should be able to see the slide. So my first point, I try to be a little provocative to stir some debate. One obvious thing that was really exciting to see already yesterday, and Felia today also reminded us of the amazing progress that we've seen in the last decade or so. We moved the field of very high redshift quasars from a few tens that we knew from STSS and the CFHQ to several hundreds. This, of course, gave us a huge statistical power, and we expanded the sample. We started to we started lots of different follow-up campaigns, basically at any wavelength. I think it would be good for all of us to slow down a little now and see if this is worth pushing for more. I'm trying to step in the panelist shoes and see what when you get a telescope time request that asks for more NTT time or VLT time to search for more high redshift quasars. Is that worth the investment in terms of telescope time? And if so, or should this be enough? Will adding 10 more quasars change the picture, or 50 more, or 100 more? If we convince ourselves that the number should be expanded, is there a privileged direction in which we want to expand? Do we want to have more sky area to have more to fill the gaps where we haven't looked yet because the wide area survey footprint was not conveniently placed or because of facilities? Do we want to go to fainter sources to expand the luminosity function over to lower luminosity regimes? Do we want to push for the high redshift frontier or other criteria that that would be useful to explore? And one thing that this is a thought I was wondering now these days that we've been talking a lot of this amazing science we are doing with the high redshift quasars. I wonder if we're fully exploiting the potential of these great statistics. Of course, you would like to have exquisite high resolution maps with ALMA of all of the 400 quasars, and the level of signal to noise in the optical spectra that, for instance, Valentina showed from the XKR30 project, right? It would be amazing to have that kind of data set for everything, right? Of course, at some point we need to stop. And I wonder, have we reached this point? Haven't we? Is there more that we can learn from targeting more quasars and with this kind of data quality? Or should we just wait for the next major leap in sensitivity and observation capabilities? Yeah, so this was my first point. Opening the floor for everybody for feedback. Yes, Matthew. Am I able to? Sorry. I think I lost. Sorry, I think I lost the. I think Matthew raised his hand.
I don't see him connected. He might have dropped.
Okay. Okay. Anyone wants to comment or chime in?
Maybe I can say something.
Yes.
For the moment, I have to say that I see very good reasons to go, for example, more for the faint end and for the very high redshift, because we really, finding even a few quasars at very high redshift will give a lot of information, put a lot of constraints on models. We have seen before that the faint end is still very, unclear, and this would be, for example, extremely important for the also for the contribution to the ionization process, for example, to understand if really there is this population of faint quasars that could contribute significantly. So I think still there are a lot of things that we would like to learn, let's say, from quasars. For example, also define what high redshift is, in the sense that there is a regime below 5.5, let's say between 4.5 and 5.5, which is still quite where the number of objects is still quite small, and so we have a hole, let's say, there. So really,
it's an unfortunate regime where it's too complicated compared to slow and this kind of universe, but then it hasn't been explored maybe as much as the Redshift 6.
So I think that there are still a lot of questions that we could answer with more objects. If you think of how many galaxies we know with respect to quasars, of course there are more, but galaxies and quasars. But still, I think that we have to investigate and to also, from the point of view of the the variance, let's say, of the properties of the object. So I think that there is still place to find more objects and to go for more for more objects.
Julien?
Yes, so I'm also on the side of more is better at the moment, especially. So here we're talking about optical near-infrared quasars, but from the X-ray point of view, for example, the numbers are not that great at the moment. We have about less than 50 quasars that have been detected so far in X-rays, mostly at the faint end. So this would really benefit from better statistics, especially in view of the X-ray luminosity function at high redshift. But also from a point of view of individual objects, I think that at the very high end of the at the bright end of the X-ray high redshift population, you'll have objects that are driven by certain mechanisms that we don't see at the fainter end, such as, for example, the inverse Compton scattering of CMB photons or some things like that. And these really, I think, are interesting and valid science. So more is better.
Excellent. I think JT also has raised his hand.
Yeah, so maybe I want to sort of extend this. So regarding the quasar luminosity function, I think especially with LSST, and so we have basically a big challenge, right? So we have now, with LSST, we'll probe to much deeper magnitudes than we had before. So we will have many more objects. And I think yesterday already there was this this notion that we need to see, like, at what magnitude a quasar or an AGN will have a host contribution. So we have to rethink our selection in parts. And in other parts, I think we cannot follow all of these hundreds of thousands of objects up spectroscopically, so that we should reserve for the high redshift part. I think regarding the lower redshift, so cosmic noon to redshift 5 or so, or even below cosmic noon, I think we will move to statistical studies. So we will basically use probabilistic quasar selection techniques, have samples on or sky areas on which we try these techniques to see how they work and if they work as intended, and then use the quasar probabilities over the entire footprint to basically constrain the quasar luminosity function. Of course, if you want to look into the quasar spectral properties or into the host galaxies, you need to do follow-up, and that will be then reserved to small tailored samples for the science questions that you want to answer.
Yeah. So there are some comments appearing in the Slack channel. Marie Wingy Lau, I'm sorry again, I'm certainly butchering the pronunciation, is eagerly waiting for the Argent Space Telescope. Currently, the best we have is WISE, and it's not sensitive enough to detect high-redshift dusty quasars. It's worth investing the money in finding the majority of these first quasars, and upcoming near-Earth object surveyors could help finding cosmic noon dusty quasars, which hopefully will be analogs of the first quasars. I'm afraid there are not great news for the Origin Space Telescope. I don't think it was, I think it wasn't particularly well received in the last decadal survey. The US collaborators would probably be able to confirm. But indeed, the lack of wide area mid-infrared sensitive facilities complement the sensitive beam observation that you do with James Webb would be particularly useful for the high redshift search in general, for galaxy evolution, and particularly for quasars. So then there is Sarah Bosman suggests that there will be there will always be value in pushing to new populations of quasars, especially to higher redshift. This is linked to the next question of the evolution. And surely there comes a point, redshift 10 or maybe, that where the problem region at least must be different. The opposite would be even more interesting, so it's worth exploring. Mazafusa brings up that the high-Z quasar community has just started to explore the dusty quasar population, which may actually dominate the whole quasar population according to recent X-ray studies. More samples of type 2 quasars and moderately dust-ridden type 1 quasars would be useful to investigate the trigger mechanism of the STSS class type 1 quasars at high redshift. I also have the feeling that we do not fully understand the quasar between the epoch of ionization and the peak of star formation epoch, but this is what Valentina was also suggesting. A large sample of redshift 4 to 5 quasars covering a wide luminosity range would be useful for many purposes. For example, post-ionization IgM, low mass stellar mass supermassive black holes, and type 2 fraction. I completely second Masafusa's comment. Definitely, one problem of the evolution that I was going to mention as my second point might also be related to the fact that we identify quasars as dropouts. So everything we know is basically restricted to a very specific population with basically type 1 AGN that are extremely bright. That might also have to do with, for instance, what Christy was presenting today about the inclination effect in the outflows. So it's certainly true that we are missing a population of AGN that is not obviously identifiable via the rest frame UV continuum and the dropout technique. I'm going through the comments, but if anyone wants to add, please, from the panelists that have, please feel free to interrupt. Manuel Solimano suggested, coming from the galaxies part of the conference, I think that having a higher number of high-Z quasars will enable more studies of high-Z DLAs, like in Simco et al., and that's very cool. And that's great, and definitely it's correct. In the sense that what Valentina was mentioning before, that if you have more sightlines, that's great for all the ionization studies. It's great for all the absorption line studies as well. Also, I think the experience with fields like 1030 that Stefano presented today is a good example where you collect, with the excuse of studying the high redshift quasar, you collect a lot of very sensitive data on basically any possible band, and then you have a great deep field kind of quality in a random area of the sky that may not be terribly hammered by pressure on array, and you get all the galaxies on the line of sight, and you can do a lot of interesting stuff in terms of galaxy evolution, or even AGN, like Stefano was presenting today, not necessarily related to the redshift 6 quasar, but on the line of sight. Andreas Feist, as a sub-question would be, do we need more bright and/or faint quasar samples? For example, I think the faint luminosity density at redshift 6 is still unknown. That's definitely something that I think everybody would agree with. And that's something that it's very important, as JT pointed out. It would be revealed. It would be pointing to the bulk of the massive black hole population. So that's certainly something that we should explore. And then Gabor Wortlek pointed at the fact that the cosmic noon, we don't have an issue with statistics, but with systematics. Different quasar selection techniques have to be tried, and follow-up spectroscopy is key. Broadband photo-Zs don't work at redshift 3. So lot of very interesting feedback. Please let me know if you think I'm missing something that happened. I think Roman raised his hand. Please go ahead.
Yeah, commenting back on what Gabor was saying about systematics at Redshift 3 and also the dropout selection. I think that's maybe I'm going to go counter to the movement here, but sometimes I think we should have more low Redshift data. That, I mean, high Redshift has excited a lot of people, and we get this incredible extruder and now this incredible ALMA data. But sometimes I think now in some cases we're at the point where you don't really know what to compare to low redshift. For example, if you do, fine structured line studies or molecular lines in high redshift quasars, you have these lines and you have these models, but you don't know if this is weird, if this is expected. Should you go back to low redshift? Well, you can compare to ULUX, but they're not quasars, right? And we have this SDSS sample. That's cute, that's great, but then you have question of systematics again. What would be very interesting is, can you mimic a kind of Redshift 6 selection on SDSS and do the same kind of analysis that we're doing, right? Because, we have this issue, for example, the continuum reconstruction, the Lyman alpha reconstruction, we're dealing with very different, you train at low Redshift and you apply at high Redshift, but you use a completely different instrument, you have different resolution. And so, when we say, oh, there is evolution, and now we have hints that there is evolution, I think we should be now very careful to, because we're just matching the luminosity, but we could match a whole other bunch of properties if we were doing things properly. And so I think there will be more and more high redshift data because it's very exciting. But sometimes maybe going back would be quite nice. And as Valentina said, there is a gap, right? There is SDSS, and then there is Redshift 6, basically. So there is a gap in between where we might, also look for something more, have a longer baseline in time, right?
Yeah, I guess a service like LSST would be amazing for that, right? Giving all the sensitive coverage, multi-epoch in a redshift range, would be easily done with the kind of sensitivity we will achieve with the LSST. JT.
Yeah, that's right. So variability, I think, is one key factor that for future quasar selections will be very important using LSST. And so variability has seen that, like, from variability selected samples, they are very pure in a sense. So you basically get very efficient selection. And yeah, and then I guess we deal with different systematics, but it would be interesting to explore them, I think.
Yeah. So maybe we can. So it seems, if I can wrap on this point, first point, I think the consensus is that more is better. We're definitely not done, and that's great. I hope that all the people reading our proposals next time are attending this meeting or will see the recordings, because that will make our life much easier. And yeah, with that, I think maybe we can move to the next point I had. Basically, again, I can probably show you just the PDF. I put this very extreme title that I think everybody would second in a Quasar and Galaxy conference. So Quasar are boring. And by this, I mean that at first look, the rest frame UV spectrum of a quasar at redshift 6, 7 looks very similar to the one of a SDSS quasar that we know now, but for very well with the hundreds of thousands of examples. And JT very nicely showed in the last talk today that how remarkably similar this is. This kind of phenomenology is through a wide redshift range, and the details, the differences are all in the details. There's a bit more shift in the carbon 4 line. There's a bit more higher fraction of BAL. I think that was from I think Valentina showed it in her talk. Weekend emission line quasar might be different, might be more common. There are examples, and we saw also in the poster session that we're trying to now measure the fraction of radio loud quasars, and we're trying to understand if these are more or less common than lower redshift quasars. I wonder if all this I mean, the fact that the quasars are so similar, it's convenient in certain aspects, because, for instance, Sarah that can use the Redshift 2 quasar to train the reconstruction of the quasar model that she will use then to do all the absorption studies. But is this something that is telling us something more fundamental? That is there something that we are not understanding of how these black holes form, how quickly they assemble? Is this a problem for modelers? It is something that puts very tight constraints on the black hole evolution, growth, also on the mechanism for jet ignition. We saw again examples of quasar extremely luminous in the X-rays and the radio bands. I'm not sure if these we know a couple of blazars at redshift larger than 5.5 or so, probably more. So are we learning something fundamental thanks to the fact that quasars are so subsimilar, or is it something that needs to be pushed to other regimes? So getting to higher and higher redshift is the only answer. Basically, we exhausted the content of information we have at redshift 6. Yes, this is not terribly original compared to what we have been discussing until now, but I stopped sharing because at least I see faces. It's easier to have a discussion. Anyone wants to comment? So in the Slack, we have some feedback. Matthew Temple writes, why would we expect a phenomenological evolution if you take a supermassive black hole and feed it with material from the ISM? Why would it care whether it is at redshift 7 or redshift 2 or redshift 0.5? Surely all it should care about is the supermassive black hole mass, instantaneous accretion rate, and recent accretion history. I see the point. Basically the point is central engine is the central engine, whatever is around. If it's a redshift, the accretion physics is what matters. If that to first order is the same at redshift 7, redshift 0. I guess it's not necessarily obvious that it works so neatly, because metallicity at some point will break, right? You need to put together the metals, you need to put together, and you need to put together the black mass of the black hole. So if indeed the black holes go through some phases of a hyper-Eddington or accretion or lower radiative efficiency, then it's not that obvious to me that the accretion physics is indeed the same through all this redshift range. I think Sarah raised her hand.
Yes, but I was going to make almost the same point as you, that at some point the metallicity cannot be so high, right? Everything points to the nuclear regions enriching extremely fast, but it can be quite instant. So the metallicity does have to decrease eventually. The opposite would be even stranger, right?
Yes, yes. Unfortunately, it seems like this happens very quickly in time, in terms of cosmic time. So we really need to push the redshift frontier in a range that is uncomfortable due to the fact that there are not so many quasars, and finding them is fairly painful. But yeah. Then Mazafusa added maybe a crazy idea, but is it possible that the Euclid and Roman will find type 1 quasars without Brundtland region, the highest redshift? The high fraction of weak line quasars and the BAS at redshift 6 is perhaps telling us that the BLR is still forming for some supermassive black hole. I would agree. I think this is a main driver of the excitement for trying to understand if properties like the weak emission line fraction is evolving, is indeed to understand if at some point you see this mechanism breaking and the Brundtland region behaving a certain somehow different way. I think there are papers even for lower redshift sources where the fact that the broad lines are weak or missing have been interpreted as the broad line assembling, the broad line region being assembling as we observe it. But to be honest, I'm not terribly familiar with the literature studying all the changing loop quasars and how the broad lines in those cases appear, if they do see the same kind of phenomenology or not. Anyone has comments on this? Everybody's shy. So I'm going through the comments in the Slack. So Matthew continued that if the quasars exist as Masafusa was pointing out, would you not expect to see such a broad region free quasar low redshift in objects which have only just turned on, which is exactly the point of the changing loops? Mary Lodi writes that there are some studies in source redshift 2 that we need to apply at high redshift to high redshift quasars and test if they allow if they follow the same behavior, and I agree. It's probably lessons that are easier to understand. It will be even easier to understand once we have big data sets of changing loop of objects, thanks to the variability studies that are currently ongoing, and there will be in the epoch of LSST. Then Karl Ferginov writes, quasar and AGN types are observational classifications, yet do we actually understand the different physical processes beyond the orientation effects that lead to these observational indicators to actually know if we should expect evolution or not? Very complicated question. I think to some extent, at least I'm trying to answer we do understand certain parts of the picture, and besides orientation, of course, there are, for instance, the question is for the fraction of type 1 versus type 2 quasars. Of course, things can easily be more complicated if you add more ingredients than just the orientation. You can add the fact that this galaxy might have, from what we see from the ALMA studies, they're all very gas rich, so you might have a significant contribution to the obscuration that is coming not from the torus, but from the ASM of the galaxy. So there might be an evolution in the fraction of type 1 versus type 2, depending on redshift. You don't need to push it to the extreme levels of redshift 6 or so, but this might be already happening at redshift 3 or 4, as we were discussing before. Definitely metallicity will play a role at some point because we trace lines that are associated with heavy elements. So at some point you should see the ratios changing and then some lines disappearing because of metallicity effects. Gabor added that there's a JT, I think, wants to add something. Feel free to interrupt.
Yeah, just one thing, and I'd be curious what others think, but from this carbon-4 velocity shift analysis, all of these high redshift objects basically do have low redshift counterparts. So basically there is a redshift 2 quasar that basically has the same carbon-4 blue shift, and you can associate it even with sort of similar Eddington ratios and black hole masses. And the same, I think, is true for basically all quasars in the bolometric luminosity black hole mass plane. And there are weak line quasars at low redshift and Ball quasars. So if we talk about evolution of the phenomenon itself, I think, I don't know if we have discovered it yet at high redshift. I would be curious to know what others think. And the second thing is that, no, I think I'll leave it by that. So I'd be just curious to know what others think.
So there are some comments in the Q&A that I was missing, and I'm sorry for that. So Girish Kulkarni wrote, probably from the previous point, some unknowns to motivate further work on redshift 5.5 and above. UV luminosity function is, and the characterization of the luminosity function and in particular completeness, multi-wavelength X-ray radio measurements, the Lyman continuum measurements of faint quasars, quasar lifetime puzzle, maybe even clustering measurements for halo mass determination, and narrow line quasars. These are all excellent points. Indeed, one of the things I was wondering for my third point on the environment was exactly that. So far, it seems from the discussion we had these days, it seems like we started from a puzzling picture with very different observational results about the quasar environment at high redshift, and it seems to me that most of it is boiling down to limitation in the methods, which might be size of the field of view, selection criteria, depth, and some cosmic variance, of course. For instance, the X-ray seemed to be a very promising way to detect this high redshift AGN, and on the other hand, of course, we are a little deprived of sensitivity, with Chandra is losing soft sensitivity, and we don't have any other obvious new facility coming. We have, of course, the wide area service like with eROSITA that we talked about today. That's great, but there are certain regimes of sensitivity that you can reach. We saw, for instance, from Romaine's talk today that using the dust continuum may not be terribly efficient as a way to select overdensities, because you will probably find an overdensity, but it's probably at cosmic noon rather than cosmic dawn. The Lyman emission, if you use C+, you're limited to very small fields because it's still expensive to do it with ALMA. And if you do Lyman alpha, you can go for much larger fields using narrowband selection, or to do the detailed picking with Muse in smaller areas. But then, as Laura today in his talk nicely showed, that if we start to get to a very neutral universe, then getting Lyman alpha might be very difficult. The selection might become inefficient. From all these studies, I think once we manage to make sense of all these selection criteria, and I think we are getting into that direction, I wonder if we're getting to a consensus that we do see these overdensities It's just that we need to really look hard and possibly combine different approaches to actually see them. And I wonder if we can hope to start to think about the next step. If indeed we accept, and maybe not, but if we agree that the environments are rich, is there a way? Is it possible that soon we will get a measurement of the mass of the halos, for instance? That would be something that all the our theoreticians in the audience and that will talk on Thursday, they will probably appreciate if we can plug all this overdensity jargon that we use into some quantitative number that they can compare with their simulations. I don't know if someone wants to comment on this. Roman.
Yes, so I think we're reaching a consensus. I think we're reaching a consensus that we're seeing more galaxies around quasars. But then I think the question is open on you know, what's the selection effect. I think we're also reaching a consensus that we see different things with different lines, as you said. And the question is, what does it mean, right? Especially for Lyman alpha, I think there is a lot to be explored here for reionization. Because on the one hand, it will carve an ionized bubble and you might see galaxies that you should not see. But on the other hand, you have probably UV radiation, which is impacting the formation of young stars. And so it might be that they are very, very special environments. And then I'm pretty sure that James Webb will paint another picture on all these quasar fields. We'll just find other stuff. So I think what could be the next step for theorists, right? It would be kind of predictions from the UV to the infrared. I know I'm asking for the moon, but I think we will soon have many observations on the same fields, and we will have different kind of galaxies selected in different ways. And so maybe something very powerful now is to look at the evolution of galaxies in the vicinity of quasars. And maybe we can sell this to the galaxy community as well as a way to, you know, look at galaxies in the reionization era, especially for Lyman alpha.
So Chiara has raised her hand.
Okay. Yes. Can you hear me?
Yes.
Excellent. So thank you for raising all of these very interesting points, and all of the discussions in Slack are all very interesting. And regarding this point in particular, I think, and so already start to think about this now, because we're going to talk, I think, more about this tomorrow, following some of the talks and hopefully also the discussion. Regarding, I sort of agree with Roman regarding the fact that we are reaching a consensus that these overdensities or rich environments are there. But one of my question mark, like biggest question marks is, what is the most urgent point? Like, what is the most urgent direction that we should take? Is it like multi-wavelength? Is it like different scales? If it is multi-wavelength, then which is best, like to go for IFU maybe to have spectroscopic confirmation instead of wasting time, quote unquote, on photometric observations or dust observations. So I think this, I wanted to discuss this point also tomorrow, because this gets me very confused still. And maybe what you say, Roman, is very true, that our simulation friends can help us, you know, with predictions of what we would be expecting, and therefore we can sort of go together with shaping observations hands in hand. And as the last point, I'm very curious to see what JWST, but also what instruments like MOONS, for example, could do with this multiplexity around high redshift quasars, because they could be complementary as well as, of course, potential variability studies, etc., etc. But this is just my 2 cents, that I think there's fields for deciding where to move next.
Okay, I think we are a bit fast over time, so it might be a good point to wrap and leave all the open points for tomorrow's discussion that I'm looking forward to. In the meantime, I would really like to thank all the speakers of today. And you did all an amazing job. All the talks were really smack on time. So my part as moderator was super easy. And all the people that contributed to the discussion today, that really made my life so much easier and brought us excellent points. So yeah, with that, I leave the floor to Roberto.
No, yes. Yeah, thank you very much. Great discussion. Thank you to all the presenters of this session and of the previous sessions. It's been a wonderful day of talks. And tomorrow we'll continue, start again at 9. And the broad general topic for tomorrow is environments. So see you tomorrow at 9 a.m. Eastern time. And thank you so much for connecting and for participating.
Bye.
Bye-bye.
Bye, everyone.
Bye.